All right, what's going on, everybody? Today we're doing another LeetCode video. This one is going to be over the problem subtree of another tree. So we're basically given two trees. They want us to determine if the tree called subroot exists as a subtree within the tree called root. So what do they mean by that exactly? Like, what is a tree? What is a corresponding tree, right? Well, with this first example, it's pretty straightforward, right? This subroot tree exists exactly right here, in terms of the node structure and the node values. It's exactly the same, right? So we would obviously return the Boolean value of true for this example, being that this tree for subroot exists within this tree root. For the second example, I think the second example highlights a pretty important clarification for the problem statement. So while subroot does appear exactly right here, notice this child or this leaf node here 2 in subroot has a child node in the root tree, in the instance of it that comes up in the root tree. So this is actually a different tree. The idea here is that, starting from this root or from this node downwards, right? So considering this 4 as a root node, it has to be exactly the same as a subroot. So with this 2 having a child node, it makes it not the same. So this example is going to be false, even though it kind of looks like it should be true. It isn't, because this 2 has a child node, so it's false. So I think that's an important kind of distinction / clarification to make. Another important, some important constraints to consider. Both of these trees are going to have at least one node, so we're never going to be given a null pointer for either root node. And then while the maximum number of nodes for the root tree is technically bigger, the root tree doesn't necessarily have to be bigger than the subroot tree. Either tree, the trees can be whatever size within those constraints, and they have no relationship constraint. So that's something important to note. So yeah, let's just get into whiteboarding, because I'm just going to go over one approach for this problem. It's going to be, I'm just going to use recursive depth first search twice, because basically the idea here is we're going to need a way to visit every single node within this root tree and then check, okay, at this node, so say we're at the root node, is the tree starting from this node the same as the tree for a subroot? And we basically just do that at each node, right? And we can use recursive depth first search both to visit every node within this root tree, and once we're at those nodes, we can use another recursive depth first search to check basically if the trees are exactly symmetrical, and if they have like the same values. So that's basically the idea. So let's just get into whiteboarding the algorithm. So we're going to first, with our recursive depth first search, we're going to visit this node here. Okay, and we're going to call our same tree recursive algorithm. So within the recursion, where we're visiting each node here, we're going to recall a recursion to see if the tree starting at this node is the same tree as subroot, right? So basically what we're doing, just to kind of illustrate this better, we're going to be taking this subroot tree, just putting it like literally right next to this tree and seeing if they're the same. Okay, right away we can see that this 1 and this 3 aren't that's not the same value. So right away, same tree is going to be false. We need to keep searching this, visiting all the nodes in the root tree. So this is going to come back as false. We only need it to be true once to exit this algorithm as true, or exit the whole function as true, rather. So we're going to keep recursive depth for searching. We're going to go down to this 2. We're going to see if check this node at 2, the tree of this node at 2, and see if it's the same as subroot, right? I could start writing this, but we can already see we're going to run into the same problem as we did before. These values aren't the same, right? So this is not going to be the same tree. So we're going to keep our recursive depth for search to visit every node in root. We're going to go this way. as soon as we see a null pointer here for our node that we're at in the root tree, we can pop back up and return false, because remember we said before that there always has to be at least one node in this tree. So we know if we're at a null pointer, like we're below a potentially a leaf node or a node, or we're basically at a dead end, right? That's like the important thing. So, okay, so anyways, we're gonna pop back up to this 2. For our depth for search, we then go down to that null pointer, which again is gonna return false. So we're popping back up, and we're gonna go all the way back up to the root node before we start searching right. So now we're at this 3, and we're going to, we can see that this is where our algorithm is gonna return true, but I'll walk through it to try and make it as clear as possible. So, so this is what we're pretty much looking at. Pretty much what we're looking at, right? So, let's do a new. This is like our nested recursive depth for search, right? To see if the trees are matching. So I'll use different colors. So let's use a blue here for going downwards, or I'll use orange actually. So we're gonna check, are these nodes, do they both exist? Yes, they do. They have the same value. Yes. So let's go left. Do they both exist? Do they have the same value? Yes. Let's go left. Once we get all the way down to a dead end here, we can pop back up with a return value of true. So this is going to be true here. And then let's pop back up. Let's use like a blue here. So we're going to pop back up, and then we would search. Shoot, I don't even know what color I used, but anyways, yeah, we'd go this way. We see a dead end, so we're going to return true. Because, I mean, by the way, it's only true because these dead ends are corresponding. It's like 2 null nodes, right? So we know if we've gotten that far, everything to that point was identical, so we can start backtracking with true. So we go back to this 4, and then we're gonna see, okay, both of the sub trees of the left and right children of this node are, they're identical for both the tree starting from the, whatever node we started on a root, and then the subroot tree. So we can basically return a true here, and then pop back up all the way back to this 3, okay, and then we're gonna start searching the other direction. So we'd go this way. We see that these 5s, there's a node here, and the 5 has got the same value, so we're gonna go this way. It's 2 null pointers, so we got true, and then we can pop back up. Okay, and then we're going to, once again, go this way. We see those 2 null pointers, so we return true. We're going to pop back up. So we compare both the corresponding left and right child trees are the same, so we have 2 trues. The value here is also the same, which we already checked, so we know that's a true, so we can pop back up a true again. Same situation here, but with these 2 child nodes with this node, that's going to be true once again, and once we see a true, we can just pop that all the way back up to the top of our recursive algorithm that was nesting that same tree search. So true, true, and finally true. So the time complexity for this algorithm is going to be big O of m times n. That's like a really bad multiplication sign, but m is going to be the total number of nodes in root, and then n is going to be the total number of nodes in subroot. So big O of m times n, and then for the space, it's just going to be big O of h, where h is the height of the root tree. That's going to be for both of our recursive call stacks. So at any given point during the execution of the method. So like the worst case, you know. So yeah, that's pretty much it. We can get into the actual coding of the algorithm now. There is a way you can do this with like hashing, and I think it gives you a big O of m plus in time complexity. But honestly, I didn't see that anywhere on the internet for C++, and I had a really hard time trying to, you know, figure that out. So if anybody figures out the big O of m plus n solution, put that in the comments, because I think a lot of people are interested in that. But nevertheless, yeah, let's go over this solution. Let's go over the code for this solution. So basically, you know, the first thing we want to do is check if we're at a null node for a root tree. And remember, the root node for the root tree will never be null. So that's going to be like a dead end. So we need to see if we're at a dead end, pretty much. So if not root, we just return false, right? Because there's no way subroot can be there. The next thing we need to do is call is same tree at the current node rat in the root tree, which we're going to keep traversing in this method. So we're basically going to keep updating our node with the recursive depth for search. So we're going to say is same tree, right? But first we're going to do it on the current node rat. So we're going to call it on root and subroot. Okay, and then if it is, obviously we can just return true from our function at that point because we only need to find it once. And it's not gonna be an else, but we also want to check if it's if that subtree exists either in the left child or the right child of the current node rat in the root tree. So we'll say if is subtree, so we'll call recursion on that outer method for root the left child, and then we just pass in the subroot tree, and it's an or, right? Because we only need to find it once. So or, and I'm noticing that this function is not capitalized there. So is subtree root right, and then pass in the subroot. Okay. So, you know, if the subtree is in either the left or right child of the current node rat in the root, we can just return true, because that means we've found that subtree in there. And then if that never gets reached, we just return false, right? Because we never find the subtree in root, or the subroot in root. So obviously we're going to need a function for is same tree. So let's just make a new private function method. That's going to be a Boolean return value. We'll just call it is same tree. And then we need two nodes, right? One for the tree, one for the first tree, and then one for the second tree we're comparing. I'll just call it P and Q. Similarly to the is same tree LeetCode problem. So is same tree star P, or is same tree node star P, tree node star Q, right? Those are our node parameters for the two trees we are comparing to see if they are symmetrical, and not just symmetrical, but identical, right? So nevertheless, the first thing we're going to want to do here is see, you know, if we're at two null nodes, that means we're at a dead end and everything to that point has been true. So we can start popping back up and returning true. Next thing we need to do is see if just one of them is null, because if just one of them is null and the other one is has an actual value, that means they're going to be different structurally, right? So we'll return false at that point. And then finally, if both of those nodes exist, we can first compare their values. And the order of these comparisons is important because you know, if their values aren't the same, then we don't even care about calling recursion at all. So that's why we're going to evaluate that first. Okay, and we want to see, and it's not an or, it's going to be an and, right? So if the values are the same, then we can proceed with our recursion. So we're going to call is same tree on P's left child and Q's left child. And then we do the exact same thing, but for their right children. So P right, and then Q right. And if all three of those conditions are true, this is going to be like at the very end of our recursion. We can safely return true because we know that these are exactly identical trees starting from those root nodes we had, or including this node, whatever node we're in. This could be a node that's deeper in the tree, but nevertheless, then after that we return false. All three of those conditions have to be met for same tree to return true all the way up to the top. So that's pretty much it for the code. Let's go ahead and run this. Once again, there is a big O of M plus N solution that I've seen in Python, but I haven't been able to figure that out for C++. So if you do, please leave that in the comments. Otherwise, hopefully this video helped you out with understanding this problem. And if it did, share it, leave a like, all that stuff. And I'll see you guys in the next video. Peace.